Okay, so let me solve this problem from the book. So this goes with the name of Snell's law. Okay, so here we have two medium. Say this is air, this is glass. Okay, at this point A, a certain distance, A from the surface of the glass, we have light. So you send light here with a certain angle. So this angle is theta 1, and this is the perpendicular to the surface. Of course, then this angle is also theta 1. And for some distance away here, okay, so let's do it this way so it looks strange. Okay, so at this point B, which is B distance away from here, and we have now light goes here, refracts and goes with a different, so it didn't go with a different angle here. So let me make this a little bit more exaggerated situation. So if I do it this way, then it will be clear. Okay, so at this point B, this is B, this angle is theta 2. So you see this angle is also theta 2. And what do we have? So this point we call C, so that we can refer to it if necessary. This distance is x, distance is d minus x. So this whole distance here is d. Okay, so this is the problem. So according to our physicist problem, physicist friends, light from here to here will choose not the shortest distance, but the path which will give the minimum time. Okay, so as far as time is concerned, light minimizes that. So we say if light can minimize it, calculus students can also minimize it. So we want to write the formula for the time it takes light to go from here to here, and we want to minimize it and see what the critical point tells us. Okay, so and in this medium light travels here with speed v1, and here, okay, with speed v2. Okay, so this is v2. Okay, so first we have to find the distances. Okay, so let me summarize this. Light from A to B will choose that path which minimizes time. Okay, so we assume that from A to C it travels in a straight line. Okay, so A and C are close to each other. Okay, so remember these gravitational waves, etc., the light being bended around the sun. Okay, so we are not looking at that. A and C are close. So light travels from here to here in a straight line, from here to here in a straight line. Okay, so much for the actual story. Now we look at this as a calculus problem from this point on. So we multiply this distance with velocity, or divide it with velocity, which will give us the time. Do you multiply distance or divide? Come on. Is everybody sleeping? We have a distance and we know the velocity. If I multiply the velocity with the distance, I take the square root of velocity added to the logarithm of the distance. Do you believe that? No? Okay, so what do I do? How do I find the time it takes? Huh? I divide velocity with distance. Okay, so so total time is this distance AC divided by V1. Okay, so this is the time. Okay, and then distance C to B with V2. Okay, so this requires that we write the distances. Okay, so this is equal to, okay, so you see I'm putting an equation here, so I don't write one equation after another equation, as students in the other classes do in calculus exams. Of course, now we don't do that. Okay, so what is this distance? This is a squared plus x squared. A squared plus x squared divided by v1. Okay, and the other one is b squared plus this thing, b squared plus d minus x squared divided by v2. Okay, so suddenly we have a function of x, and this function of x apparently, since I'm taking squares, this makes sense for all possible values of x. But in my problem, x can be 0, it cannot be negative, it doesn't make sense otherwise. Okay, and x cannot be larger than d. Okay, so it has to, light will not go there and come back. Well, at the, maybe such setups exist, but in this problem we restrict x between 0 and d. Okay, so 0x d. So this is the function to minimize. So let us say total time is t of x. Okay. Okay, so this is the function to minimize. So let me look at the derivative. So t prime of x is equal to, I'll do this as 1 over v1 times here x over a squared plus x squared and minus, well, you take the derivative of this one, minus will come from here, so I put it here. I'll again write it as v2. Then we look at this d minus x over this thing itself, b squared plus d minus x squared. Okay. Now we want to equate this to 0 and solve. So before we start crying, we realize that there is something nice here. X over this number, x over this number. Okay, this length over this length is what? Tangent of this? Sine of this, okay. So we are not sleeping, I woke you up. Okay, so that is sinus. Let's do it this way. Okay, so this one, we realize that this whole thing is sine of theta 1. Okay, and similarly, this side divided by the hypotenuse is sine of this angle. So this thing is sine of theta 2. Okay, so this gives us a condition for the optimal time. Okay, so so the light chooses the point C, so that sine theta 1 over v1 is equal to, because if this is going to be equal to 0, okay, sine theta 1 over v1 is going to be equal to sine theta 2 over v2. Okay, so this thing is known as Snell's law or Snell's law. I don't know how it is read. Okay, so this is again a typical optimization problem. The crucial thing is to set up the problem and find a function which expresses what we have in mind. Take the derivative, equate to 0. Okay, and as I said, this part you do mechanically. After you equate that to 0, then you start thinking. Okay, so in this case, we already found a very nice result, because we were trying to understand how light finds this point C. So we were trying to understand the length of x, but it turned out that we can do it this way. Okay, any questions? No? Okay. So we did these things, so let me see. Okay, I have 2 long problems and a longer problem, so if you don't stop me, you'll have 5 minutes for the quiz. Okay, so my next question is a very typical and a very famous problem in calculus. Okay, so the problem is this. I take this end of the paper and put it here. Okay, so this corner must come to this edge. I fold it here. Okay, and I measure this length. Okay, so obviously this length depends on where I put this corner. I can put this corner anywhere I like. If I put this corner here and I crease it, I get infinity, okay, because it's a mathematician's paper. It has infinite length here. If I take this point and put it here and fold it here, this fold goes to infinity. So if I take this over here, if I put somewhere else, but you see, I cannot do anything better than this. I can manage to fold it like this. So this is the maximum value, okay? So if I put my finger here, I can take this end and put it anywhere in here, and the value, the length of this crease changes. And since we don't have anything else to do in math department, we wonder what will be the minimum length of this crease. Because I already found out that the length goes to infinity. If I go down here, it goes to infinity, okay? It is finite here. So what is the graph of this function? Is it infinite at this endpoint, or is it infinite? Is it finite at this endpoint, or minimum at this endpoint, or it takes its minimum somewhere in between? Okay, so that's the problem. So another problem. So we have paper like this, and we do it like this to denote that it is infinite. Okay. So let's see, let me draw a convincing picture here. Okay, so convincing picture required something like this. Okay, so if you are wondering what these are, they are my cat. Okay, so this corner is this corner, so that's why it is 90 degrees. It is this distance here which I am trying, so let me do this properly. Okay, so this goes like this. Okay, so this distance is x. Well, you can choose this as x, you can choose this x, you can choose this x. Okay, so that's why in the solution, if you say x equals 5, it doesn't make sense to anybody, because everybody can choose a different function and a different parameter. So for some reason, I chose this x, and I chose this length. I call this length L. Okay, so then this is L minus x. Then I have secondary variables. This side is A, and this is D. I want to minimize D. This side is B. So this side I'll use as A minus B. And I notice in the figure that just because I put 90 degrees here, this is this side. Okay, I'm taking this side and folding it. So this side is the same as this side. So maybe, okay, so actually these two triangles are the same, not in my figure, but in real life, because I'm folding this. So this triangle falls into here. So these two triangles, this one and this one, are the same. Okay. So find where, or well, we don't want to, what is the minimum, what is the minimum length obtained in this folding? Length of crease. Okay, so it is D. Okay, so that is minimize D in the figure. Okay, so this is also A. Okay, so all we have to do is write D in terms of X. Okay, so for this we have to use a few equalities, so it's not immediate, but if you play around, there are several. If you draw a better picture, then you will see identities more clearly. Okay, so there are several triangles that you can use, and eventually you come up with the formula. So, and there is obviously not only one method of attacking this. I'll just show you how I did it this year. Okay, so I notice here that in this triangle, d square is equal to a square plus x square. Okay, and then a square is, I think I take this triangle now. Okay, so let's see, 1. In triangle 1, I have this. And in this second triangle, apparently I'm using this, okay. A square is equal to L square plus A minus B square. This is from triangle 2. Now, if you open this up, you see there is an A square here. Okay, so that cancels. Then you have from here, A is equal to L square plus B square, and you have minus 2AB here, which you took here, and then divide by 2B. Okay, then where is this? I think it is from here now. This is triangle 3. In triangle 3, you have B square plus L minus x square is equal to x square. So this is triangle 3. So again, x square cancel. And here you have b square equal to 2lx minus l square. Right, I take this to the other side. Okay, so this is what I get. Okay, so this is the other thing. So finally, I find, okay, now I think from here on I can calculate. Now I can talk about f of x is equal to d square, and d square is equal to a square plus x square. So let me do this. And instead of a, I put this thing. Okay, so L square plus b square over 2b square plus x square is x square. Okay. Okay, we simplify this. So I will not do the simplification, and eventually we get this. Okay, just simplify this. You get L x square over 2x minus L plus x square. LB square. Maybe I should do one more thing here. Put this thing, okay? B square is equal to 2lx minus L square. Okay, so putting these things, you get this function. Now, this is my function, but I check that x can be, in my example, x can start from 0 and go to L. Okay, so. Okay, so this is the, no, x cannot go to L. Okay. Well, x can, why not here? For some reason, in my notes, I said x goes to, x can go to L, but x cannot be 0. Okay. If x is small here, if I fold this, okay, if x is small, if I fold this, I will never make this part touch this part, okay? So I should start from halfway so that at least it will touch it this way. Okay, so that's why from the figure. So this from the figure. Okay, if x is small enough, I try to fold this part. So you see this point is this point. If I decide to take this small, then this part will not reach over to the other side. So this is the function to minimize. When I minimize it, I will find d square. And square root of this is the answer to the question. Okay, so let's see what we do next. Okay, so next I take the derivative of this function. Okay, so f prime x is equal to, okay, so everybody knows how to take the derivative, so let me just write the result. 2x squared 4x minus 3l over 2x minus l squared. And we want to equate that to 0. Okay, so you see x equals 0 is a critical value for this function, but x equals 0 is meaningless for us because our function has this domain. Okay. So the only solution in this domain comes from here. Okay. X equals 0 is a solution to f prime x equals 0, but 0 is not in our domain. Okay. The other solution is x equals 3l over 4. 3 over 4l, which is in our domain. Okay. So we now next, no matter how complicated or how simple the problem is, the next step is again standard. You calculate the function at this critical point and at the end points. Okay. So when the function approaches here, you see we cannot put x equals, well, maybe I should do it this way. We cannot put this value because it will make the function infinite. Okay. So limit. So endpoints. Since this endpoint is not in the domain, we take the limit as parameter approaches to that endpoint. Limit x approaches to L over 2 from the right of f of x is infinite. Okay, so this becomes something over 0. And the other endpoint is in the domain. I can put it here and I can calculate f of L. So f of L is this whole crease. You just take this and make x equals L and put it here. So you just calculate it either from right triangle or from here, and you'll find that this is 2L squared. And critical point, f of 3 over 4L. And you calculate this. You put this number here, calculate this. This is 27 over 16L squared. Okay, so this is 2L squared. This is less than 2L squared because 2L squared here will be 32 over 16. Okay, so this is small. Of these three numbers, this is smaller. Okay, so that's what calculus gave us. Eventually, we got three numbers. Minimum of these three numbers is the minimum of this function on the whole interval. This is smaller. Okay, so mean value of f. Okay, so remember that we minimized f, not d. In a minute, we'll take square root of this. Minimum value of f is attained when x is equal to 3 over 4L. Okay, so we solved the calculus problem. Now we read the question again. What is the minimum length of this crease? Our function is square of this thing, so minimum is square root of this. Answer. The minimum crease has length. Okay, square root of this. 3 square root 3 over 4L, where L is the, okay, so you see I'm here using L, but L is not mentioned in the question, So I have to tell for which reason I'm using L, where L is the width of the paper. Okay, and this is and this is approximately, so this number is approximately 1.3 L. Okay, so that's what we do in math department. Okay, I'll mention the next problem, and then we'll have our quiz. I will not solve. You don't have time to solve this one, but I'll just mention this. Okay, any questions on this? Evde düşüneceksin, size ödev olarak veriyorum. And next week I'll check if you thought about it or not. Okay, so so weekend joy. So we have a swimming pool like this. Okay, so we have a swimming pool in the shape of a circle for some reason. Okay, this is the center and this is the diameter, A, B. Okay, so let's make it dramatic. A baby falls into water at the point B. This is a mathematical baby, so when she falls here, she doesn't fall here, she falls just at the point B. Okay? There is a lifeguard. Well, then when I say there's a lifeguard, you say let the lifeguard figure it out. So you stand at point B, diametrically. No, you stand at point A, diametrically opposite the baby who is drowning. Okay, who is about to die. Okay, and you swim. I have numbers here, but let's make it numbers, letters. A meters per minute. Well, on the weekend you can try several numbers here. I'll give you that freedom. And walk and run B meters per minute. Okay, so you can try this with different numbers. So what is your strategy? What is your strategy to reach and save the baby in the shortest time. Okay, so you have to swim a little bit. So in my thing, your strategy is to find this point C, so that you swim to the point C and then run along this. You can do it the other way around, but it doesn't matter. Okay, so and this angle, I call it theta. So find theta. So find the point. That is, find the point C such that you swim to C, then run along the arc CB, and this path should take the shortest time. Okay, so at the weekend, try these things, and you will find a surprise for this. But I will not, of course, tell you what the surprise is. If I tell you what the surprise is, it would be like our surprise quizzes. Yes?